Another important section in integration. In my previous video I discussed about the integration basics and how do we integrate a function when we have x to the power something other than -1, what is the general formula, and how to get the general solution for a differential equation. We discussed that part, as well as how do we derive the equation of a curve, equation of a function when they have given the differential equation. I have added the link in my description. You can follow up if you missed my first video in integration. So this is about my second video, so enjoy the video. So today I am discussing about the finding the area under a curve with the support of integration. So I will focus quickly. So let y equal fx be a function. It is required to find the area under the curve y equal fx in a given region. So they will give you a function with the small sketch of the function on the Cartesian plane, and they will give you a limitation, a particular bounded region that you need to evaluate the area under that part. So let's see how we can do that. This is just the idea, how do we derive a certain proper method, a formal method or a methodical manner to find out the area under a curve with the support of integration. So here I'm sorry, I'm kind of sick. So you can see clearly we have a function y equal fx, that is a general function, just a general case I am going to consider. We are going to evaluate this shaded region. So you can see my smallest possible value is x equal to simple a. The maximum value of x will be x equal to b. So the area is covered, bounded by these two vertical lines. One is x equal a, other one is x equal b, and the other horizontal line is going to be the x-axis, and the other remaining side will be the under the curve. Under the curve is the boundary. So what do I do here? I am going to consider a small area part of this region, not the complete shaded region, but a small region which is denoted as MNPQ. So, and the other important part is that whenever this P point is moving along the curve, this MNPQ area will be changing. So that will change time to time. If P is somewhere here, let's say this point P x comma y is somewhere here, then the region is somewhat smaller. When it come up to somewhere here, as shown there, somewhat bigger. When it go to somewhere here, the shaded region is somewhat more larger. When I go to B only from A, I get the complete area. So for this case, I have considered the general point P x comma y with the coordinate x comma y on my curve. So let's see how do we do that. What do? I am going to consider a small change in x direction to get the idea better. So take a look at the next slide. So I have considered a small shaded region under the curve such that point P will be right on the curve there, P. The coordinates will be x comma y. So this coordinate will be x comma y. When this is increased by small amount of x in positive x direction, that is considered as delta x amount. So the new x coordinate of this capital T will be x plus delta x, because this length is delta x up to here x, so this will be x plus delta x. As well as when x is increased by delta x amount, you know under the rules of differentiation with the first principles method, when x is changed by a delta x amount, y will be changing automatically by delta y amount. So then coordinates of capital T will be x plus delta x comma y plus delta y. Now we will try to find this area with the support of this method, right? And I am going to consider three regions. One region is PQRS rectangle, which is this region area. If I find out that area, I can find out that area by multiplying the length by this height or the breadth. Then I can find the next region which we need to find the area PQRST or PQRT, which is the area under the curve, which is the exact answer. So the other part is I am going to consider this UQRT rectangle, that is also rectangle. I can find it using my length into breadth method, quite easy. So the idea behind this will be, if I compare these three areas, the smallest rectangle, area under the curve, area somewhat above the curve, which is also a rectangle, you can see that the interested area under the curve is in between the area of these two rectangles. So if I find the area of them, area of PQRS will be, length is delta x, height is y into delta x. That will be the area of PQRS rectangle. Then the area of PQRT, I consider it to be delta A, just a notation. I took it as delta A. Why? This is a very small amount of area. When it is very small, we use with delta notation. And area of this UQRT rectangle will be delta x multiplied by y plus delta y. The height is y plus delta y. So you can see this result is right there. Then I divide each and every term by delta x amount. So I first one divide by delta x, second one divide by delta x, third one also divide by delta x. So then it will be simplified up to somewhere here, y less than delta a by delta x less than y plus delta y. So we are almost in the final derivation. So you know that this delta x is a very small amount. Then if I decrease this delta x amount somewhere closer to this x, that will be very small. Then at last it will come up to x. Then it will be negligible. That means when delta x approaches to 0, automatically y plus delta y will approach to y, as delta y also goes to 0. Then according to the limit theorem, you know that when limit delta x goes to 0, approaches to 0, delta a by delta x become dA by dx. Okay, as well as y plus delta y become y, finally we get that dA by dx equal to y. What does it mean? The rate of change of area with respect to exchange is equal to the function. So we are done with the derivation. That means when you integrate the given function, if you integrate the given function, you can find out the area under the curve, right? So my final result, I consider it like this. The rate of change of the area under the curve is equal to the length of the moving boundary, that means the function. For an example, find the area under the curve y equal 6x to the power 5 plus 6 between x equal minus 1 and x equal 2. So obviously when you are trying to find out the area under the curve with the support of integration, please try to have a small sketch of the curve. Then you will get a better idea what is the region bounded by the curve, x-axis and the two limited x values. That will support you to get the answer correctly and easily, because we have the visual diagram. So I have a sketch there. I consider this is my sketch, y equals 6x to the power 5 plus 6. This is my sketch, and I have marked the two limit values, x equal minus 1 the lower limit, x equal plus 2 will be the upper limit of our region bounded. Then I have considered a small point p x comma y somewhere on the curve for the general case. Then let's see how we can find this area, right? I denote the area bounded by the curve x-axis and the two limit x values as capital A, right? Then what is given? dA by dx equal to y. This is our result. Y means 6x to the power 5 plus 6, which is the equation of the function in this case. Then we try to apply integration. So dA by dx become a 6x to the power 5 becomes 6x to the power 6 divided by 6. So 6 by 6 cancel off. X to the power 6 additional to 6, x will be added y. If you have constant term, it will be followed by x to the power 0. When you integrate x to the power 0, it will be x to the power 1, right? Therefore 6 becomes 6x plus c. This is the general solution of this differential equation. Therefore c should be there as an arbitrary constant. Then we will see how we can find the simple c value. We can see according to the diagram, according to our curve on the Cartesian plane, when x equals -1, area becomes 0 because it is the initial point. When the initial point is at a point, we don't have a certain area, that is negligible. Therefore we can use this substitution here to find the value of simple c. When x equal to -1, capital A becomes 0, area becomes 0. So 0 equal to -1 to the power 6 plus 6 into -1 plus c, which will lead to simple c equal to 5. Finally we get that area is equal to x to the power 6 plus 6x plus 5. This is the general solution. This is the general result that you can use to find out the area from x equal to -1 up to somewhere on the curve. In this case we have to find the area up to x equal plus 2. So what do? I substitute x equal plus 2 in this general solution. So when I put x equal to there, I get the answer as 81 square units. So it is done. Now we have found the area under the curve with the support of integration using this particular method. This looks bit long for you, I know that. That's why we have some more formal methods in the future. So this is the general way you can find out the area. What is the method? If I summarize, first take the given function as dA by dx equal to the particular function y, integrate it, then use a substitution there to find the general solution for the area and substitute the other limit given. So most probably we will use the lower limit substitution to find the simple c value, then use the upper limit to find the actual area under the curve within the bounded region. So this is done. So I hope you got a simple idea about how we can apply this integration method to find out the area under a curve. So then I hope to focus a little bit more to get a much better result for this integration. So standardized formula to find the area under a curve using integration. We will see how can we go with the formal method. Suppose that the area between the curve y equal fx, x-axis, and the lines x equal a and x equal b to be found. Then what do we do? This is my general case. Y equal fx function, x equal a, x equal b, x-axis under the curve. This blue color shaded region to be found. Then I consider my general case, dA by dx equal to y. In this case y equal fx, general function. Integrate fx, then dA by dx become capital A, area. F of x become f of x. This is simple. If this is capital F, I just took it as the integrated result of fx function. No problem with that. And don't forget the additional arbitrary constant simple c there. And you already know that when we substitute the lower limit to the given result, area will be 0. Why? This is that initial point. At the initial point we don't have an area. Then 0 equal to f of a, capital F, right? F of simple a plus c, simple c equal to minus fa. So now we can substitute the simple c equal minus fa to my general result of finding the area. But we need to find the area between x equal a and x equal b. Then substitute x equal b to this result. It becomes a equal to fb minus fa. Done. This means whenever you want to find out the area under a curve with the support of integration, what you have to do? Integrate the given function, substitute the upper limit to the result of integration, substitute the lower limit to the result of integration, get the difference of them. When you apply this result, we don't use simple c there anymore. There will be no arbitrary constants anymore, right? Then finally we get the final result as fb minus fa, and this is denoted as fx. This is the integrated result function of fx function. Lower limit is simple a, upper limit is capital P. Take the difference of them after substitution. That will give you the area under the curve above the x-axis as well as between the x equal a and x equal p line. So we are done with this part. I hope you enjoyed the video, got the knowledge how to manage integration and apply it to find the area under the curve within a given bounded region. If you have any doubts or questions, please comment below or forward me for an example. I'll give another question for you to try out. So try yourself, check what will be the answer, you can comment it. So I have added the process of doing that as well as the answer. Check your answers whether you are getting the same answer as I have shown there. Then this will be the second video of my integration. This will be ended. Then I will add one more video relevant to integration. We will be discussing much more better questions and better results, better derivations relevant to integration. Therefore keep in touch with my channel, and thank you for joining.